Anyone? All right, so I'm assuming there are no problems, but if there are any, please mention them. Okay, so C, when C is 1, it needs to be in 2's complement, and we need to check magnitude. Oh, so the thing is, the fun part is you need not actually check the magnitude at all. So if you observe the numbers in your 2's complemented form, the except for the sign bit, rest of the numbers automatically follow one particular order. Like if you look at them, only the beginning 3 bits from LSB, you can see that they are actually in an increasing order. So you can directly compare those bits, and you can be fine. You need not actually convert it back to regular form from 2's complement form. That makes sense.
In the test bins, how do we assign a 2-bit or a 2's complement number?
You need not technically assign anything specifically as a 2-bit complemented number. You just use it as a regular number because as far as your design is concerned, as far as your synthesized Verilog is concerned, it doesn't know whether it's 2's complemented or it is regular unless you specify it to be a signed number or something. So because that is the case, it lies upon you to actually make your design smart enough to understand that, and that's what you are trying to do with least possible effort here. So even in your test bench, you need not actually say that these are signed numbers. You can write your logic wherever there is self-checking part, uh, saying that, okay, this particular thing, if the sign bits are like this, then the rest of the things need to follow this particular order. So yeah, no conversion is required even in your test bench, even in your design, no conversion is required. And you need not specifically mention that there are 2's complemented numbers. Does that make sense?
Yeah, kind of. So when we're checking it for the 2's complement, can we just kind of reverse the greater than less than check, and it'll kind of account for the 2's complement, or no?
I mean, you can. Technically, that's what is happening. But when you look at the numbers, they are not like that. For example, give me 1 second. I'll try to tell this in a better way, I guess. All right. Let's see. So I'll try to do it this way. Can you guys see this?
Yes.
Yeah.
All right. So let's say we have numbers -1, -2, -3, -4, -5, and so on. So if you look at their 2's complemented representation, it's generally like 1, 1, 1, 1, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, and so on, right? And in here, this is your sign bit, so it doesn't matter because you have already checked for it. But if you look at the rest of the bits, they are increasing from down below, right? So 0, 1, 1 in general is less than 1, 0, 0, and 1, 0, 1 is less than 1, 1, 0, 0. Sorry, 1, 0, 1 is greater than 1, 0, 0. So if you compare those numbers, so if you are in this binary state, this number is automatically greater than this number. So your regular logic is still applies there. So you just need to compare these 3 bits and say that, you know what, this number is greater than this one. So -1 is greater than -2. Does that make sense?
Yeah, that was what we discussed in class. I think I just confused myself, so thank you.
Yeah, so you need not actually convert them, or even in your test bench, you need not do anything. You can directly do something like this and it works. Is there any other problem with lab so far, or anything that has been done so far?
I was a little confused on like how to do the self-checking test bench. So I just put in a bunch of values to get the answers, but could you go over that real quick?
Yeah, so in this case, so inside your initial begin, right? So for example, initial begin, you have, in order to do it exhaustively, you have 2 or 3 for loops, right? One for the value of C, one for A, one for B, right? Have you started?
No, I didn't do that. I just put in different values for A, B, and C and then waited a few seconds. Then
Oh yeah, I mean, that works too, but so what's happening inside this for loop is basically it's doing the same thing, like it's giving values. And if you have like found 5 here after assigning the values, let's say assign statements happen here. I mean, they're not technically assigned, so they're just equal to statements. So if those statements happen here and you wait for certain value of time, what's happening is it is going on and assigning some values and waiting for some time. So instead of manually doing it, for loop is doing it for you for all the values, right? So even if you did not use a for loop, you might have used something like this, right? So in here, you need to write certain logic that is at this part. So what this logic basically says is, it will calculate everything possible with respect to your actual design, and then it will say whether it is equal to your value that is found in the output here or not. Actually, you know what, I'll give you a better example. So for example, we have come across something called an adder, right? So we have two numbers. It's a half adder, A, B, and outputs as CO, right? So let's assume we have a half adder, and this is a module that you have declared, right? So what you do in your test bench, let's assume we call this module HA. So in your test bench, you have module TB underscore HA. You have whatever declarations. So you have your HA module called here, call it UUT, and you make the connections accordingly. So dot A TB underscore A, dot B TB underscore B, dot C TB underscore C. I'm assuming C out to be C. So, and dot sum as TB underscore sum. So this is sum, right? So what's happening here is you're creating these variables called TB underscore B, C, and S. And these are the inputs and outputs that are present in your test bench. So your test bench is essentially a higher level Verilog file. So this is your TB underscore HA, inside which you have your half adder. And this has A, B, C, and S internally, but there are some wires connected here, which are called TB underscore A, TB underscore B, TB underscore C, and TB underscore S. Is this part clear so far?
yeah.
So what happens here is whatever changes you want to make or whatever value you want to send in, that happens only at this particular level, right? So TB underscore A and TB underscore B are the only things that your test bench can actually control, because what happens on TB underscore C and TB underscore S is dependent on what your design is. In this case, it depends on your half adder. So there is really no specific way for you to give values to TB underscore C or TB underscore S unless you change the values of A and B. So these are the only things, these are the only two variables that are in your control. Does that make sense?
Yeah.
All right. So let's say we have our initial begin, right? So initial begin, and we are trying to give values here. So what we do is, let's say we waited for 5 time units, and then we gave values like tv underscore a is equal to 1, tv underscore b is equal to 2, and then we waited, right? So we waited for another 5 time units. So the way your self-checking would work in this case is I would write an if statement, right? If tb underscore a plus tb underscore b is not equal to, right, tb underscore sum comma tb underscore c. So what this particular syntax does, tb underscore sum comma tb underscore c, is, oh sorry, they should be reversed. So so what this syntax does is it concatenates those both terms beside each other. So essentially the output of this is your carry bit followed by your sum bits, if that makes sense. Do you guys understand that?
Yeah, that makes sense.
Right. So what I'll do is I'll say tb underscore c comma tb underscore s here. So if this condition is not met, then I'll say dollar display error. So one thing to note is instead of tb underscore c and tb underscore s, I could have still written carry or sum, right? So I can still write c or s and that would still count. But because our test bench does not recognize that particular thing, I'm like, okay, this is not recognized by the test bench, so I'm good, right? So what this condition is doing is basically you are sending your data through your test bench, and the output that you're getting is based on your design. So that's the reason you can reliably say at this particular point that if this condition is not met, because they're technically supposed to be equal. So if that condition is not met, then your circuit is not functioning correctly. So you're basically doing a self-checking thing at this particular statement. Does that make sense? Do you guys understand the
Yeah.
self-checking part better?
Yeah, thanks.
So to quickly double check over it, those curly brackets in this case wouldn't be concatenation. It's just using the test bench to go to your main file and then do the calculation.
No, they are still concatenation. That's the syntax you used for it.
Oh,
I mean, yeah, the curly braces are a syntax for concatenation of your bits, or they basically say you are considering these bits together, right? So it's like if you look in terms of your hardware, it's like you're bunching these wires together, if that makes sense. Is that clear?
yeah, I think I just need to look at self-checking stuff more.
Mm-hmm. Yeah, don't worry. I mean, it can be tricky. Like even now, if I want to make some test bench, I need to be really attentive and try to find some logic about it. And it all depends on what logic you're trying to apply, and there is no one specific way to do that. So whatever you write in here is the logic that you are thinking of, right? So for your comparators, the logic might be different. For your adders, the logic might be different, and so on. So it'll get easier over time. You'll understand things better. All right. So I'm assuming you're okay with test benching and all. If you're not, you can always leave me a mail or a message, and I'm more than happy to help. But moving on, today we will go through lab 4, and then after that I'll be checking off your lab 3s. So if checkoffs for everyone are not possible, you can still email me or leave a submission along with your video, and that would still work. And in this case, because you're not putting it on the board, a screen capture would still work as a video. But make sure you have something on the screen that says that it's you, like your directory or your name or UID or something like that. All right. So moving on, for lab 3, what we'll do today is we'll understand the concept of clocks. Then we'll understand what flip-flops are and how they are represented in Verilog. While we do that, we'll come across non-blocking assignments, and we'll compare what non-blocking assignments are with what blocking assignments are. And then we'll quickly go over the week 1 part of the lab, and that is the part that is due for checkoff next week. Is that clear for everyone? Do you guys understand it?
I think so.
All right. So moving on, let's see what clocks are, right? So apart from the fact, or it's not a fact per se, apart from the knowledge that clocks are oscillating signals, does anyone have any idea about what they are in your design in general? Can anyone define clocks?
I know that when it comes to circuits, clocks are like between 0 and 1 signals, and then when it's rising or falling, that's when values can change depending on how you make a circuit.
Yep, that's one way. Yes. So depending on so your clocks generally, in general, oscillate between 0 and 1. But you can have any signal to be your clock as long as you have your design built in that way, right? So the signal can be any signal. But the most general definition of clock is, in your design, you want something to give a timing reference for various activities to happen. And by activities, I mean various signal changes or inputs happening or outputs happening and things like that. So you want something that will basically measure the amount of time it takes. And depending on what clock you're using, that measurement can happen in different ways, right? So like you said, yes, they are a parameter for CPU clocking rate, and yeah, they measure in cycles. Yes. So coming back, say suppose you have something like this. This is the most general form of clock, right? So you have a square wave with 50% duty cycle, right? So 50% duty cycle. So that's why it's a square wave. So you are on for the same amount of time, or you are at level 1 for the same amount of time as you are at level 0, right? So this is the most general form of clock. It's a square wave pulse, and it oscillates between 0 and 1. So whenever your clock goes from this 0 stage to this 1 stage, right, this transition that you see here is called the rising edge of the clock, right? So this is called a rising edge or a positive edge. In your Verilog, you call it pause edge. And whenever you see that your clock is going from 1 to 0, so this falling transition is basically called a falling edge or a falling transition. And in Verilog, it's called a neg edge. Is that clear for everyone? Do you guys understand these concepts so far?
Yeah, you're saying that the pause edge and neg edge are both like keywords?
Yes, they are keywords in Verilog. Yes.
Okay.
So yeah, so coming back to what clocks are in general, right? So say suppose you look at your computers or your phones or things like that, you always hear like your processor is rated for 2.8 gigahertz or something like that, right? You have some number with some frequency that's going on. So what this frequency basically means is that your processor can sample things, or your processor is oscillating at that particular frequency at the very maximum level. So beyond that, your processor does not have the power to actually sample the data. It does not have the power to reliably say, this output is correct, right? So say, so again, coming back, this is called the frequency of your oscillation. And if you look at this particular square wave, frequency can be calculated by calculating the time period, right? So wherever there is repetition happening, so in this case, this particular window, right? So this window that you see keeps on repeating itself, right? So it goes from 0 to 1, and again it goes from 0 to 1, and so on. So it goes at 0 to 1, and it keeps on repeating. So this particular window takes, say, suppose t amount of time, right? So it is on for t by 2 and off for t by 2. And this t amount of time is basically, if you do 1 by t, that is basically your frequency of operations. So that is the frequency at which you can sample your data. That is the frequency at which various operations happen. And everything on your digital design, if it is synthesized for that particular frequency, then everything happens at that particular frequency. Is that clear for everyone?
Yeah, that makes sense.
All right. So when I say everything gets sampled at that particular frequency, the reason I say that is because most of the designs, most of the modern designs, they make use of something called a flip-flop, right? So a flip-flop is an edge-triggered device. So what I mean by edge triggered device is whenever there is an edge in the clock, so whether it be positive edge or a negative edge, depending on how you design it, it is that particular edge flip-flop, right? So if it's a positive edge flip-flop, then you can say it's a pause edge triggered flip-flop, right? So most of the designs that you see in today's things have flip-flops that are, edge sensitive or edge triggered, and within one time period at any given point in time, so within one time period of your clock, there exists at least one edge that is happening, right? So if you consider this to be your time period, then you have a negative edge in there. And if you consider this to be your time period, then you have a positive edge in there. So between any inside any time period, you can find at least one edge. And because your flip-flops and your circuit get sampled at that particular edge, you also call it the sampling rate at which your flip-flops are functioning, or your memory is functioning, if it is synthesized to that frequency. Does that make sense? Do you guys understand that concept?
Yeah, I think what you're saying is just regardless of what the timing happens to be, you're going to have one edge inside of every period.
Mm-hmm. That is correct.
Okay.
All right. So even though you did not understand that concept, I think you will in a few moments, because we'll understand what a flip-flop in general is, right? So moving on, let's say this is a device, right? And we'll call it flip-flop, but we'll understand why we do that. And it has an input called D, or data, and it has an output called Q, and then it has another input called clock. So what I'll do is I will put a small triangle here. So what this triangle is basically saying is that this particular device operates at the edges of the signal where it is present, right? So it is present at the signal of clock. So this particular device operates at the positive edge of this particular clock. If it is negative edge, then I would have used a bubble here, right? But I don't, so it is essentially a positive edge triggered device. And I'll call it a flip-flop. We'll understand how it is functioning and what different methods are and stuff like that. But as of now, this is a device at a very high level. Does everyone understand this? Do you have any questions or things so far? No? All right. So moving on, the functionality of this device is in English, in general terms, says that whenever there is a rising edge, right? So at every rising edge, my Q or the value of Q uh, is, or the value of D is replicated at Q, right? So that is the functionality of this device. And in general, if you think about flip-flops are considered memory elements. And the reason that is the case is because whenever there is a positive edge, the value of D gets inside this flip-flop and gets reflected at the same time at Q, but it remains in the flip-flop until the next positive edge. So for that particular moment of time, you can store a bit of data inside your flip-flop. So if it's a 1-bit flip-flop, you can store 1 bit of data inside the flip-flop from a positive edge to the next positive edge. Is that clear? Is that functionality clear?
I think so.
All right. So how would we write this in terms of our Verilog? Right. So how would we write this particular functionality in terms of Verilog? So yeah, again, we have our declarations of module. I'll call it flip-flop. So a flip-flop like this is called a D flip-flop or a delay flip-flop or a data flip-flop. So I'll just name the module as DFF. I have D, Q, and clock. And inputs are D and clock, and output is Q, right? I have these declarations, and then I have a module somewhere here. How do you think the reactions are happening, or how do you declare this particular module in your flip-flop? Any ideas?
Maybe do like using an always block on D and Q, or on D and CLK, and then just check to see if clock is high. And if that's the
So,
case, then set Q equal to D.
all right. So let's see. We use an always block. That is correct, right?
Okay.
So we have an always block with begin and end, right? So the thing is, what does our functionality say? What is the signal that is guiding us to the change, right? In our lab 3, we knew that whenever any of the input changes, your output should be changing, right? But in this case, you change your output only when there is a rising edge of the clock, right? Irrespective of what your value of data is. So your data doesn't really matter in your sensitivity list, but your clock does. Does that make sense?
Yeah, that's a fair point.
All right. So again, the clock entirely doesn't matter because you don't care for a falling transition. You only care about the rising edge. So in order to specify that particular part, what we'll do is we'll write pause edge clock. So whenever there is a positive edge of the clock, your circuit is performing. So this always block takes care of that. So it says whenever there's a positive edge on the clock, certain operations should happen. So what is the thing that happens when there is positive edge of the clock? How would you write that in terms of Verilog? Anyone? I mean, the functionality is right here.
It'd just be Q equals D.
right? So if you just do Q equals D, that should basically be your flip-flop. Does that make sense to everyone? Does everyone get this point, right? So at every positive clock edge, your Q is nothing but your value of D. So whenever there is a rising edge of the clock at this particular input, your D is getting stored in here as well as getting replicated in at the outside. Does that make sense to everyone?
Yeah, so just to clarify, when it comes to Verilog code, the positive edge and negative edge will do the stuff for calculating when it goes to 0 to 1 or 1 to 0 for you. So you don't have to do anything in that regard.
No, you need not.
Okay.
So this part, Q is equal to D, though, operations wise, it is correct, right? So whenever there is a clock statement in your always sensitivity list, whenever you have an edge triggered nature, you tend to write a different kind of equal to. So that equal to looks like this. Its symbol is less than or equal to, but it is called a non-blocking assignment operator. So what this is doing is, it in this particular case, it is exactly equal to Q equal to D. It is called Q equal to D, but there are two different kinds of assignment operators, right? So non-blocking assignment in general does not block any other operations that are happening inside your always block. So we'll get to that. But before we do, is this clear or is this confusing? So instead of equal to, we are using something called a less than or equal to, or a non-blocking assignment statement. Is that clear?
I'm a little fuzzy still on what the non-blocking actually refers to. Could you maybe touch on that for a sec?
Yeah, I will get to that, but just with the syntax, is that clear?
Oh yeah, the syntax is clear.
All right. So yeah, we'll understand why equal to is a blocking statement and why non-blocking statements exist, right? So let's think about two always blocks, right? So there is an always block. It has some values in here, right? And then I have things like B is equal to A. Then I have C is equal to B. And then D is equal to C, right? So this is my always block. I have begin and end. And then I have another always block with some values. And I say begin and end. So instead of equal to's, I have non-blocking assignments. Right? I have these two blocks. So the way these two blocks function defines what things are, right? So what have we learned about always blocks so far? So whenever there is some trigger that happens, something that is present in the sensitivity list that happens, everything in the always blocks get executed. And how do they get executed? They get executed sequentially, right? So they get executed statement after statement. Is that what we have learned so far?
I think
All
so.
right. All right. So let's assume these are the values present in your A, B, C, and D, right? Before the always block is triggered, right? So at the very beginning, before the triggering of always block, let's assume these are the values that are present in there, right? So as soon as the trigger happens, so in this case, the trigger is nothing but this statement, right? So it could be anything. It could be a POSIX clock, it could be A, B, C, D, or something like that. whenever the trigger happens, your first statement gets executed, right? So the first statement says your B is equal to A. So your B value now changes. So now B is equal to 1 in this case. Does that make sense? So whenever
Yeah,
the
that
trigger
makes sense.
happens, this statements get executed first, and that says B is equal to 1. And after this statement gets executed, it comes to this statement. And what happens there? Your C is assigned to B, but the value of B now is 1. So your C also changes to 1, right? Do you guys see that?
Yeah.
Yeah, I see that.
Similarly, your D also changes to 1 because the value of C is 1 now. Because these things are happening one after the other sequentially. Does that make sense?
Yeah.
All right. Now let's look at this one, right? So in case of this assignment, the sole purpose of non-blocking statements is to make things happen at the exact same time. So the definition here is whenever there is an always block, whenever there is trigger, the always block is triggered. Uh, all the statements with non-blocking assignments. So all statements inside this always block which have this symbol on them happen at the exact same time, right? So again, if your A is 1, B is 2, C is 3, and D is 4, when trigger is happening, right, at this point, your A is getting assigned to B, right? So your B, the new value of B is 1, but at the exact same time, B was getting assigned to C. So at that particular point in time, your C also has changed to 2 and your D has changed to 3 because they were all happening at the exact same time. Does that make sense?
Yeah, okay, that makes a lot more sense. So it's basically like forcing concurrency.
Yeah, kind of. Yes.
Okay.
So I
Okay.
didn't want to use the term concurrency, but yeah, that's where that's actually kind of right. Right. So it yep.
Oh, sorry. So, quick question: if you also had like a mix of other equal signs, would those happen concurrently while the
No. So
sorry,
so
not concurrently. Sequentially, while these ones would work concurrently
right. So if
together.
I have something like this, right? So if I have something like that, these both operations happen concurrently, and this one happens after that. Does that make sense?
Yeah.
All right. So now, in case of this particular design, the operation of B is equal to A happening actually is not it's kind of restricting the rest of the operations to happen. So in a way, this equal to sign is basically blocking these things from happening. So that's why it's called a blocking assignment statement. It blocks the rest of the assignments from happening. And in this case, whenever you have signs like these, they don't block anything. They make sure that everything happens at the exact same time. So they are called non-blocking assignment statements. And that's where the name comes from. Is that clear for everyone?
I guess I'm wondering, why do we need those for the clocks? Because isn't the only thing that's happening is that Q is getting assigned to D and that's it?
Yes, but in general, if you have, yeah, so that's why I when I was going through it, I said in this case it would work exactly like Q is equal to D. It would work exactly like Q is equal to D, and we are fine. But your compilers in general get mad when you have something like clock and you have a regular non-blocking assignment statement, regular blocking assignment statement sometimes, but most of the times they should be fine, right? In this case where just Q is equal to D is happening, you should basically be fine. But you'll understand why you're using a non-blocking assignment statement when you have a few more signals added to it, and you will get to that point in a few minutes. Is that clear?
Yeah, that cleared it up. Thank you.
All right. So is everyone okay with, or does everyone understand what blocking and non-blocking assignments are?
Yeah.
Yeah, I think so.
All right. So what we'll do is we'll understand a tiny concept of your timing diagrams, and then from there we'll get to resets, and from there we'll understand your lab 3, right? So let's say you have your same flip-flop, right? You have your flip-flop where you have D and Q with the exact same functionality, the triangle with the clock, right? So at every positive clock edge, your D is getting replicated at Q, right? So let's say this is your clock, right? So this is your clock. It goes from 0 to 1, and you want to find all the positive edges at the very beginning. So these are the positive edge points. Right, so these are all the rising edges that are present in here. And then say suppose you have your value of D. So your input can be anything, right? So in this case, let's assume your input goes between 0 and 1, and it looks something like this, right? Say suppose this is your input. Right, say your data looks like this. It need not be exactly like that. In all the cases, it can be anything. So I'm assuming it is like this, right? So how would my queue look, right? So to begin with, before the first clock edge is happening, you don't have any data sampled. You don't have anything so far. So this would just be a red line in your model sim, or in general, we describe it using something like this, right? So you don't know what the output is. So until the very first positive clock edge, you don't know what is happening, right? So what does our functionality say? At every positive clock edge, your data gets replicated at your output. So at this particular clock edge, your data is high, so your output will also be high. So at that clock edge, your D was 1, so your Q will also be 1, right? And then it will remain in that state until it encounters the next positive clock edge. So until the next positive clock edge, it will remain in that state. And at that positive clock edge, it will get sampled again. And in this case, our data is 0, so it will go back to 0. So it will be at 0, and it will remain there until next positive clock edge. Does that make sense to everyone? Do you guys understand what's happening here?
Yeah, I think so.
All right. So what happens at this positive clock edge? So what is the output that I'm expecting from here until next positive clock edge? Anyone?
Just one to be high.
Right. So at this positive clock edge, because your data was high, the high point gets sampled, and it will remain at that particular location until next positive clock edge, and so on. It continues as long as the clock exists, right? Does that make sense to everyone?
Yeah, I think so.
So yeah, this is called the timing diagram of your. This is called the timing diagram of your flip-flop. And in general, if you have you know a Verilog file written in your quarters, and you have your test bench generating a clock and some random data, this is the file that you see in your model sim. So given this, there is a small concept, or not a small concept, but instead of flip-flops, there could be something called a latch, right? So a latch is a device which kind of performs like flip-flop, but not exactly. So the latch operates, instead of at the edge, it operates at the high level of the clock, right? So whenever the clock is high, that's when your data gets sampled. And whenever the clock is low, the state is retained. So how does that particular thing look in our waveform, right? So again, these are the positive edges, right? So until the first high state is experienced, you still remain in the state of limbo where you don't know what's happening. So the signal, you don't know what's happening in here. And then from whenever there is this high level, your data is getting replicated. So what we'll do is we'll also make note of the falling edges, because those are the endpoints of the high level, right? So in between these lines is where your data is getting replicated. So in between those lines, your data takes this particular shape. So your output would take the exact same shape. Does that make sense?
Yeah, so in this case, it's like instead of just sampling in the one point, it's sampling whatever it is that D is at every point while the clock is on.
Yes, that is correct.
Okay.
So instead of it being edge triggered or edge sensitive, now it is level sensitive, right? So whenever the level is high, your data is getting sampled. And then it will remain in that state until the next change causing event is observed. So it will remain in this negative state until the signal goes high again. So when the signal goes high, the next time your data that is present here will get replicated. So in this case, this is getting replicated, and it will remain in this state until the next high state, and this data gets replicated. So that data is getting replicated, and it will remain there until the next high state where you have the negative value. So this data will remain there. Does that make sense to everyone? Do you guys understand this?
I think so. One thing with the latch, is it the same? Does it basically look the same as the flip flop?
So internally, your flip-flop basically has two latches connected back to back with each other. So if you look at the internal design, I'm pretty sure professor will go through that in the class, but at a very high level, if this is your flip-flop, right, this is at a very high level. So if this is your flip-flop, internally you have a positive edge triggered latch and a negative edge triggered latch, or sorry, positive level triggered latch and negative level triggered latch, and they are kind of connected in a feedback loop. And this is the output that you are kind of getting. So because these latches are positive and negative level triggered, you have this very fine line called the edge in between, and that's how you sample that edge. Does that make sense?
Cool. Thank you.
All right. So given the knowledge that we have so far, what we'll do is we'll get to our lab 4, right? In our lab 4, we are basically trying to build a stopwatch. So what we are doing here is we are trying to calculate. So initially, at every positive clock edge, we are trying to say that, our design is changing values, right? And then in our next week of lab, what we'll do is we'll try to calculate the number of cycles it takes per second, and then at every 1 second value, we'll try to change the values, right? So far in this particular week, what we'll have to do is, so in this particular example that we have looked, right? So we have learned that Q is equal to D, is basically our flip-flop, right? So if we do something like in our declarations, instead of it being D and Q, right? If we do something like 3 down to 0 D, 3 down to 0 Q, and clock is still an input that is 1 bit wide, right? So if you do something like this, it would create 4 flip-flops behind one another, and they would basically take in a 4-bit data and give out a 4-bit data, and all of them would perform exactly like the same thing. So it would be 3 down to 0, it would be Q is 3 down to 0, and so on. Does that make sense to everyone? Do you guys understand it? Anyone?
Sorry, my headset cut out just a second ago, and I
Okay.
didn't really hear much.
Oh, okay. So you could always make a multi-bit or a flip-flop that can store more amount of data by giving something like this, right? So you can always have 4 bits of data. So what your compiler does is it creates 4 flip-flops behind one another, each of them 1 bit wide, and you're essentially storing 4 bits of data there, right? So now your memory element can store 4 bits. So if this is happening, right? So if something like this exists, so what we can technically do is we can store something like 0000 in these 4 flip-flops, and then at every positive clock edge keep on increasing this value by 1 bit, right? So at this particular clock edge, say suppose you have stored in 0000, and then at this clock edge you are incrementing it by the value of 1, and then incrementing it by another 1, and so on, right? So if you do something like this, you can essentially build a system where you can store the values from all zeros to all ones. So essentially what you're doing is you are able to count these many number of clock cycles. Does that make sense to everyone?
Yeah, I think so. So it's basically like you're putting you're forcing the adder
Correct.
to just bring in one value each time the clock edge happens.
Correct. So what's happening in terms of your design is you have your flip-flop, you have some input, you have a data coming out, and again a clock, right? But this data is basically being fed back, right? And these both are 3 bits wide or 4 bits wide, and this is being fed back into an adder where the other entrance of this adder is 1 bit 1. So you're always adding 1 bit, and that is being fed into this. Does that make sense?
Yeah, that makes sense.
All right. So we are trying to design something like this, but there is a small condition over it. So the condition basically says our flip-flop cannot exceed the value of 9, right? So in this case, 9 is basically 1001. So you have to design your Verilog in such a way where these things are obeyed. So what we'll go through is we'll try to write what this Verilog is, and then I'll explain a small concept called reset, and then I'll leave it to you guys to figure out the rest of the part, right? So if you look at the same diagram, right? So you have your flip-flop, you have your output, you have your adder, then 1 bit 1, and then that is going in here, right? And then there is clock. You want to design something like this. Again, everything before your always block is declared. Let's say you have always at passage clock, right? So you have something like this. So how would you write your logic in this case? So how would you write your logic in this case? Milk the sorted.
So I think you would start with doing your Q non-blocking D, and then from there you throw the Q value into the adder, which will then feed back into D.
Right. So in this case, you don't see an explicit statement for D at all. So what I would do is I would do something like this. I would always store a value of Q plus 1 into Q at every clock cycle. Does that work? Or to have better precision, one take B1, right? So it'll always store a value of one incremented Q at every positive clock edge into Q. So whatever my initial value of Q is, I will store one bit more than that. Does that work?
Don't you
I
risk
think it would, but
overflow that way?
Pardon me? I could not hear you.
Oh, sorry. Don't you risk overflow that way?
Correct. So we need to go from 0, 0, 0, 0 until value of 9. So 1, 0, 0, 1, right? So what we'll do is we'll say if we'll put a conditional statement over it. So we say if Q is equal to 1, 0, 0, 1, reset Q to 0, else do this. Does that work? Does that solve an overflow issue?
I think so.
Sure.
Right. So this is exactly the design that you're trying to build, right? So this is actually, pretty much 80 to 90% of the design that you're trying to build. So in general, flip-flops or any sequential circuits for that matter, along with clock, Q, D and Q, have another signal called a reset signal. So what a reset signal does is whenever this signal is encountered, your Q or your outputs get reset to a value that you already know. So in general, it is, in general, what people do, or in general, what designers do is whenever there is reset, your Q gets assigned to 0, right? So in your design, when you're trying to build your circuit, you want to include this particular signal as well. And that signal can be programmed in any way, right? So you can say if my reset is high, then Q is equal to 0, or if my reset is low, my Q is equal to 0. Or if I encounter a negative edge of reset, my Q goes to 0, or positive edge of reset, Q goes to 0, or whatever, however you feel comfortable. And make sure your board, accepts that particular behavior, because it might be difficult for you to, get the edge triggered thing on the board with reset. I would go with level sensitive as of now. So I would create a signal called reset, include that in this design, and I would try to solve this. So in your lab 3 for first week, you will design a circuit that looks like this. So essentially you are getting an output of 4 bits wide binary number here. And if you look at the files section of your canvas, you should find something called a BCD to 7 segment display Verilog code. So you'll use that code at this particular point, and then you'll assign the outputs to a 7 segment display on your board. So BCD to 7 segment display code here, and then you'll assign the output to that particular part of the board. And that's the first week part of the lab 3. Does that make sense to anyone? Everyone? My bad.
Sounds good.
yeah.
All right. So if you guys have any further questions on this, I can answer them. If not, I'll start checking off from 10, 15, like in 5 minutes, I'll start checking off.
For the checkoffs, what do we want to have pulled up just to make it smoother?
Right. So I'll be seeing your Verilog, your test bench, and your simulation.
Okay. If our simulation doesn't actually output anything and just checks that the values come out successfully, is that good enough?
Yeah, I mean, that should work. Even if it's not self-checking, that should work. But make sure
Oh, it
if
is.
it's
It
not-
is self-checking.
okay.
It just
Uh,
doesn't like because it's self-checking. Like it just exits if there's an error, and then it prints out that everything was successful at the end if there wasn't an error.
Oh, I would still want to see the waveforms if that's okay.
Oh, okay. Yeah, I got you.
All right. Let's see.